Проба, 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 проба. Добре. Проба, проба. Ще тече, ето той се чува само тонната страна. Едно.
Едно, две, три. Едно. Добре.
Ти колко сигурно говориш горе?
Колкото трябва.
Could everyone take a seat, please? Could everyone take a seat, please? Preslav.
Hey guys, we might very well go towards starting this meetup today. First of all, we have a dedicated channel in Slido where you can post your questions, slido.com. It's mobile friendly, just enter the channel's name, DSS, and we can talk there, like more interactively. We have a second mic as well, so we can use this as well. There is a stream, a live stream, so there will be questions from out of this room. So that's the point of the Slido. You are welcome anytime to join. Now, should we start? Yeah, so first of all, I'd like to thank very much Preslav for joining us tonight, because it's practically the last night before he leaves for Qatar. So thank you very much, Preslav. And as the agenda says, I will do a short update on the state of play in data science society. What happened recently? There are some cuts there, but everything is fine. Now, as most of you know, we are building a hub to connect science, business, and education. And it's been almost a year since our first meeting of the core team to start building things. And we have definitely made some progress. We've captured audiences and partners from all along the spectrum. Probably I'm missing some here. For example, Vivacom, we are here thanks to Vivacom, and they should definitely be included for next update. Next week we are making a meetup with Skyscanner as well. So there's a lot of involvement going on even in the hot summer days. And we'll be moving on even more fast in the coming autumn. Now, this is the core team that's moving most of the things. We are a bunch of volunteers. Again, probably not everyone is present because it's a moving crowd, very much so. And what we've made so far, it's basically a lot of meetups all along the range of learning methods, algorithms, concrete applications like recommender systems, information retrieval, some tools like MATLAB. We had a dedicated workshop made from the MATLAB representatives for Bulgaria, and we've browsed some of the sectors that do data science application. But generally, we are focusing on a very broad range of topics, and the scope is wide. So everybody is welcome to these meetups, to the volunteer crew that's making things happen, and not only meetups, because we have more than 25 volunteers at this point. We are starting since June 4 projects that I will tell more about later. 4 projects dedicated to data science, to analysis, to visualizations, etc. Now, not only this, we are currently based in Sofia, but we cannot consolidate everything here. So we are engaging communities all around Bulgaria. Stara Zagora, Burgas, Varna. For the last event, there were streaming events locally in Burgas, Varna, and Stara Zagora. Also in Plovdiv, that were basically attended. So, but this is growing, and we are talking to several cities in Romania. If we pan out the map a bit, there is also Barcelona talking to us, and we are trying to connect people from all around the place. The last meeting was with a German speaker. We have Preslav here from Qatar, so that's the direction. That's the direction, basically connecting not only the business and education and science in Bulgaria, but bringing a lot of the knowledge, a lot of the know-how, a lot of the connections broadly in geographical perspective. Now, what we are doing basically, one of these is the meetups that we've made most of. We are also doing workshops and hackathons. Very soon we'll release the first datathon in coordination with some of the hack guys in Bulgaria. We are moving very fast in the field of conferences. We've been to BurgasConf, thanks to Maria. We'll most probably join VarnaConf and HackConf in the autumn. So, and potentially we'll build a dedicated data science conference in the near or not so near future. Let's see how this pans out. Now, as I told you, there are several projects going on at this point. The first and very fast growing team is for analysis of education data, which is gathering analytics and building some very interesting insights that we'll be releasing in the autumn. We're building open source libraries, not only for NLP, but for a broad range of topics. There's a project to build tools for visualizing open data. And the last meetup was also dedicated to open and linked data. And we are trying to build a tool, our website, to facilitate the interaction not only within events, but also online in real time whenever someone needs collaboration or knowledge sharing, to be able to do this through the website. This is coming. So far the website is more like a business card, but we are building onto this. For any questions, you can reach us on datasciencesociety.net, through Twitter, LinkedIn, Facebook, YouTube, and all of the we are not only streaming, but we are also recording these events. So all of the resources, all of the presentations and video materials are live on our website. You can join us anytime. And for the event today, we have you can post the questions either live or through Slido. So thank you very much. Once again, thank you to Preslav, and I will invite him to join us here.
Yes, sir.
Okay, can you hear me now? Okay, good. I was planning to jump directly into my talk. Is there some microphone here, or is it good? Okay. So I was planning to jump directly into my talk, but maybe it's good to tell you something about Qatar, because there was this Qatar, our speaker. Okay, let me tell you something about Qatar, right? So I'm coming from the currently. Well, okay. I graduated here in Sofia, from the Sofia University, and I did a PhD in the University of California at Berkeley. Then I tried to come back in Bulgaria, and I chose an unfortunate time. This was the beginning of 2008 when the crisis started. So, you know, I decided to hide from the crisis for a while, and this for a while continues up to date. I've been in Singapore, and now I'm in Qatar. I was in the best of the Western world, in the best of the Chinese world. Now I'm in the best of the Arab world. Okay, and I was in the best of Europe. Okay, so where is Qatar, right? Here's where Qatar is. As you can see, Saudi Arabia on the left and Iran on the right, and who knows what is on the north. So this is the peninsula, this is Doha, and this is where QCRI is. QCRI is the Qatar Computing Research Institute. This is the West Bay, and this is our building, the Tornado Tower. This is the same building at night. And they are building us a new building, and we are probably moving there in the fall. The institute has several groups, and I'm in the Arabic language technologies groups. We don't do just Arabic, we do language technologies in general. We want to be a leader in Arabic language technologies and to do important research. And we have two main kind of research directions. One is multilingual processing. This is transcription, translation, speech recognition, machine translation, and so on. We collaborate with Al Jazeera on that, which is based in Qatar. Another big project that we have is on interactive question answering and dialogue systems, because as you know, so far, you know, as of now, the World Cup in 2022 in football, in soccer, is going to be still in Doha unless they change something. You know, there has been a lot of scandals in that respect. And we are building a dialogue system to help tourists get around and get information and so on. And then we have other things like OCR for the local libraries, because there are a lot of interesting historical documents in Arabic that we want to recognize, to make searchable educational applications, information retrieval and so on, and all kinds of you know, tools and resources for Arabic language processing. So this is our team. Actually, this is part of our team. We're probably about 25 people now, and we have a lot of very distinguished scientists coming from Carnegie Mellon, from Microsoft Research, from Fondazione Bruno Kessler, and so on. Yeah, so this is what we have achieved in the 3 years so far. We have a very strong collaboration with MIT. We have a 7-year collaboration. We have joint projects with them. The institute as a whole has a startup together with MIT, actually with Stonebreaker, who recently won the Turing Award, which is the highest award, kind of the Nobel Prize of computer science. This is not our group, another group in the institute. Yeah, we work with Boeing, with Mayo Clinic, and so on. Yep, we rock. Okay, so let me go now to the talk. Okay, I'm going to talk about the web, using the web as a training set in an implicit way, and you're going to see what I mean by that. And I'm going to focus mostly on a linguistic problem, the syntax and semantics of noun compounds. So how many of you here know anything about linguistics or natural language processing? Okay. I hope that the rest will not be bored. I mean, for the rest of you, the beginning and the end, you know, might be more entertaining, and kind of in the middle, it might be kind of less, but let's see how it goes. Okay, so the big dream of the field of natural language processing is this. You want to make computers capable of understanding human language, right? So you want to be able to say something to them and, you know, build a system that, you know, understands what we tell them. They kind of can respond to us, and so on and so forth. And you have seen this in a lot of science fiction movies, and this is supposed to happen in 2001, but, you know, we are a bit behind schedule. Well, where are we really, right? So there are different fields of natural language processing. Well, in terms of information retrieval, right, we have Google, which is great. In terms of machine translation, we also have Google, which, 2011, right? They had a system that can translate poetry, right? Wow, okay. So you can put all translators out of business. In terms of question answering, we have Watson, IBM Watson, who has won Jeopardy, right? Which is quite a breakthrough. In terms of dialogue, we have Siri. In terms of speech recognition, we have Siri and Google. In terms of generation, we have news. We have computers that write automatically news articles. And by the way, we are consuming texts in major newspapers written automatically, fully automatically by computers every day. We don't realize it. And this is going to grow. I'm going to show you more examples on that. Okay, the Turing test has been passed. This is kind of a test set up by Turing to check whether, you know, artificial intelligence has been achieved or not. So it's done, right? I mean, all the problems are solved, and okay. Well, probably not really. I mean, Siri is great, right? I mean, but doesn't really always understand. Well, I mean, it really tries to help, right? Or, I mean, okay, if you ask kind of a complicated question, it can do amazingly well. How much woodchuck could chuck wood? Okay, it depends on whether you are talking about African European woodchucks. Wow, great. European woodchucks, okay. 8 European restaurants close to you. Google Translate, I mean, it fails. There are many stories. One of them is kind of amistad, which is like, you know, friendship in Spanish, and then, you know, it's murder in English for whatever reason. Well, machine translation can fail in other ways too. I mean, okay, and the Turing test hasn't really been passed. I mean, there has been a lot of, pretty much the next day that after the, I mean, there was this kind of annual conference, I don't know, maybe like 50 years after the, I mean, they really wanted to make news and this is kind of discarded. Okay, so I have talked a little bit about the, I mean, I'm going to talk a little bit about the past. Most of the talk is going to be about technology that is here about the present, and at the end, there is going to be kind of more provocative things about the future, about the direction that I think we are going. Okay, the past. Very, very brief history of natural language processing. So it all started in the 50s. Actually, the very first problem that was addressed was machine translation. Well, part of the reason was that immediately after the Second World War, the Soviet Union went quite strong in you know, space technology and so on, and kind of in the US they were afraid they're falling behind, so they started like stealing a lot of technical literature, and they thought, okay, maybe we can automate the translation, so kind of they focus on automatic translation between Russian and English, right? All this stolen technical literature. And there was a lot of money put into this, right? And then at some point, the American government said, okay, let's you know, put distinguished scientists, evaluate the research so far, and see where the taxpayers' money went. And the report actually was quite skeptical. It said, okay, machine translation is not here yet. It's not going to be around in the kind of near future. If it's going to be around, it's not going to be economically viable. I mean, not immediately. So they kind of said, okay, you should stop building machine translation systems. What you should be doing, you should be focusing on basic research. You should understand how language works. You should try to solve the little problems that are going to get you there. You should define milestones, and then you should return. And now we are in the position where kind of, you know, you all use Google Translate and all that. You know that we have kind of, you know, achieved some of this. But anyway, this kind of AUPAC report has done a lot of damage on the funding on the field, but at the end of the day, it was for good. And then in the 90s started, I mean, the whole field was dominated by rule-based systems, and in the 90s started a statistical revolution where the idea was, okay, you have a problem that you want to solve. What you do is you just get a very large text collection, you compute some statistics over it, and you build a system in that way. And this has revolutionized the field. This was only possible because this was possible for two reasons. I mean, the models were around, but there was a lot of data and there was a lot of computational power and a lot of storage. This was just not possible earlier. Okay, so this is where we are. We are at this point, we have web-scale corpus linguistics, and this is things that people are doing. So, for example, this same machine translation problem that they're talking about. So Google is using the entire web to build a language model, kind of, you know, to smooth the translations. That's why when you translate from, say, from Bulgarian into English, it's much better than if you translate from English into Bulgarian. There are other reasons for that as well, but kind of, you know, the machine translation has two components. One that cares about preserving the meaning, and another one that cares about smoothing the translation. And actually, if you ask professional translator, and kind of this second component, you can train it on the entire web, okay? And, okay, in terms of translation, right, translators say that you always balance two components. One is staying faithful to the original meaning, and the second one kind of make it, you know, smooth, sound nice. I mean, the kind of translators say that good translation is like a woman, right? If she's beautiful, she's not faithful. If she's faithful, she's not beautiful. Sorry. Okay, if you speak French, right, it's like la translation. Si elle est belle, elle n'est pas fidèle. Si elle est fidèle, elle n'est pas belle. Okay, sorry. Okay, so going back to the you know, the statistical revolution, right? There has been this influential paper, early paper in 2001, which was called by Banco and Brill, Scaling to Very, Very Large Corpora for Natural Languages Ambiguation, where they have taken a particular problem, the problem of spelling correction. So you have pairs of words that you know from, you know, in advance, a priori, that they are commonly confused, like principle and principle. People, you know, can be maybe when they are typing fast, or maybe they just don't know the difference, or for whatever reason, they are, you know, confusing them. And the task is you have a context, a particular context, you need to say, is this the right principle or the wrong principle in this particular context? So basically, it's a classifier. So what you need to do, and here's an example, the teachers and the principal of the 137th school, Angel Kanchev in Sofia, Bulgaria, share their experience, blah, blah, blah. And actually, here in this context, right, this is principal, right, of the school, kind of director, kind of, the main boss of the school, and you can see this because this school and other kinds of keywords around learning. And here we have another example, another context. Bulgaria plans to carry out ambitious reforms, blah, blah, keeping the principle of the rule of law. And actually here, right, that's probably the other principle. I mean, because you have law, you have, this is set by a president, by a politician, kind of, politicians like to talk about principles, kind of not those principles, the other principles. So, I mean, and basically you can build a classifier, right, that looks into the context and tries to predict the right thing. And I guess that most of you know how to build this such kind of classifier. It's just basically you have some weights for the neighboring words, and you just see accumulate the evidence and you vote. Okay, it's kind of a simple problem. What is interesting about this problem is that you can get a lot of training data. I mean, if you take, for example, newspapers, right? You don't expect many mistakes there. So and you can actually end up with a lot of training data. And this is what they have done. So here, there is a walk linear scale. So you see 0.1, 1, 10, 100, 1,000, right? This is like a billion words of training data. And here's the accuracy, how correct the classifier is. And so they have used 4 different classifiers. It's not important what these 4 classifiers are. What is important is the trends that you see in this graph. So, okay, here's what you see. You see, first of all, that even if you train with a billion words, I mean, you don't really saturate. I mean, the more data you get, the better the algorithm works. Something else that is very interesting is kind of when you have little data, the best algorithm is this one, but when you have a lot of data, it's actually the worst one. Another thing that you can see is kind of, the worst algorithm turns out to be the best with a lot of data. And there is also a lot of difference between those 3, but then with a lot of data, they're pretty much the same. So basically their message is, you know what, guys, you should not waste your time trying to, improve your algorithms over here with a little bit of data. What you should do is that you should go and get more data. Because if you have a lot of data, then it doesn't really matter which is the best algorithm. I mean, which is the algorithm. Kind of the algorithm is kind of secondary. And this is a great idea. The question is, does it apply to other problems, right? And okay, this is a similar kind of graph done by Google, as I told you about using a language model for machine translation. And here you see a similar kind of graph. It's again kind of walk linear, trained over the entire web. There has been another paper in 2004 and then a follow-up in 2005 by Wapata and Keller, where they used simple n-gram models, which is basically how often you see on the web a particular word or a particular pair of words, and they just look at those statistics and try to solve different problems. And basically they have 8 different problems. I mean, machine translation candidate selection, when you have different candidates, which one is the best in the particular context, when you should put a definite article or indefinite or you should not, and noun compound interpretation, and noun compound bracketing, and putting the adjectives in the correct order, and this same spelling correction problem, and so on and so forth. And basically, what happened is that for 3 of those problems, using simple counts, how many times I see this word or how many times I see this pair of words together, as opposed to that other pair of words, they achieve results that are significantly better than the best previously published ones that are coming from supervised algorithms. For 2 others, they have results that are comparable, not significantly different, but also not worse. And for 3 others, the last 3, they could not improve. And I should say those are all kind of unsupervised or maybe like widely supervised, indirectly supervised. The idea is that, okay, what I mean here, unsupervised classification is called clustering, okay? You have to have some level of supervision if you want to have classification. But in those models, there is no training data. But there's kind of a little bit of supervision that tells you which direction you should go. Anyway, their conclusion was that the web should be used as a baseline, which is each time you address a problem about language, you should first see, okay, how far can I get if I just see how many times I have this word on the web, or these 2 words on the web, or those 3, which is super simple, right? And if the super smart algorithm that you are developing cannot beat that baseline, you are probably not doing very well, okay? This is what they have proposed. So I think, and actually I have shown in my work, and other people have shown in related work, that we can actually do better. And in this talk, I'm going to show you how one problem from this group can be moved into this group, and another problem from this group can be moved into this group, okay? So, in particular, I'm going to focus, I'm going to show you that you can achieve much more if you use the so-called surface features. I'm going to tell you what this is. If you use paraphrases, if you use linguistic knowledge to test different kinds of hypotheses. A very nice colleague, Adam Kilgariff, has passed recently. He died out of cancer. And he has written an interesting squib in computational linguistics called Googleology is bad science. So Googleology is kind of, you know, this pejorative reference to the science of, okay, let's forget about linguistics. Let's just see, okay, how many times I have this word or this pair of words, kind of people taking this literally. What I'm going to show you is, okay, I still think that the web is an important source of information, but I think that it should be used smartly. I mean, I think that we should use linguistic knowledge. You should kind of, you know, using paraphrases and so on, you're going to see kind of, you know, smart uses of the web that go beyond the engram. I'm going to focus on noun compounds. So what is a noun compound? Well, there are different definitions. And the definition that I'm going to use is a sequence of nouns that function as a single noun. So here's an example like healthcare reform, or plastic water bottle, or colon cancer, tumor suppressor protein, and so on. And of course, in some languages, those can get, you know, complicated because, you know, noun compounds in German are just written as one word, Corpus Linguistic Conferenz, right? It's just a spelling convention. In Bulgarian, we also have compounds, but they are a little bit different, like Къща музей, човекомесец, нармак, and so on. And there, as you can see from here, there are like basically 3 problems. Okay, there are 3 problems about noun compounds. The first one is very obvious from German, right? Is the segmentation. You want to, you know, tell what is the boundary between the words. And here, healthcare, you probably also want to segment it into health and care. Sometimes there is ambiguity. Another problem is syntax. Syntactic ambiguity is, okay, plastic water bottle. Does plastic modify water or does it modify bottle, right? Is it a plastic water or is it plastic bottle? And then the last one is semantic, okay? So what is, for example, that water bottle, okay, that's the bottle is container of water, and plastic water, kind of here plastic is material. I mean, this kind of some semantic interpretation. And I'm going to talk about the syntax and the semantics of noun compounds. And of course, you know, in German those things can get, you know, much. Okay, I'm not going to try to read this. Okay, noun compound syntax, right? So linguists like to write trees, and the ambiguity, the syntactic ambiguity here can be represented as a tree. So here we have plastic water bottle, so we have water bottle, and you know, and plastic modifies the whole thing. So you have like water bottle maybe made from out of plastic, and here we have some kind of plastic water. I don't know what is plastic water, maybe like water that tastes like plastic or something like that, and then it has something to do with bottle. And of course, the left, this interpretation here on the left is the correct one. Another way to represent this is with bracketing. So plastic water bottle, here we have a right bracketing, and here we have left bracketing. And of course, this has some implication to semantics. So water bottle made of plastic, this is what, you know, the left interpretation is, and the right one is bottle that contains some kind of plastic water. Okay, so basically, if you get the syntax right, I mean, if you believe in this syntax, right, then this is something like water bottle made of plastic. So this kind of has some restrictions on the semantics. Okay, how can you solve this problem? One way is to use, the Wapata and Keller approach, just different kinds of statistics. So you can say, okay, maybe you go on the web and you say, do I see on the web plastic? Okay, I want to check whether plastic modifies water or bottle. Okay, do I see on the web more frequently plastic water or plastic bottle? Okay, and then you compare those two quantities, and if you see if plastic bottle is kind of more frequent than plastic water, then you go with this kind of interpretation. Or alternatively, if you believe not in the dependencies, not in the adjacency, you can kind of say, okay, is it plastic water or water bottle? And of course, you can kind of have probabilities, and you can have point-wise mutual information, chi-square, and all that. Those are all kind of simple statistics about how many times I see this word or this pair of words. So something that I have observed is that in many cases, you can find the target noun compound in another context where you have some kind of surface markers that mark, that tell you how you should be reading this. And also you can generate different kinds of paraphrases, and you can inject linguistic knowledge. And I'm going to show examples of this. First, the surface features. One indicator is the dash. So you have, for example, sales cycle analysis, and you need to say, is this a left structure or a right structure? If you find it somewhere on the web with a dash between the first two, that probably tells you that those two words go together, so you probably have a left structure. And the same thing, donor T cell. If you find T cell as one thing, then this is probably a right structure. The same thing with the genitive, possessive marker, world's food production. If you have it here, then probably food production goes together. This is a right structure, or cell cycles analysis is probably a left structure. Capitalization is another thing. You want to say, okay, is it Plasmodium vivax malaria? Which way does it go? If you find it somewhere on the web with, lowercase here and uppercase here, that's probably a left structure. Another thing is the slash. Okay, so if you have like leukemia, lymphoma cell, you want to see this, and is this a left structure or right? If you find it on the web with a slash here, this means that those are two alternatives, which means that leukemia cannot modify lymphoma, it should modify cell. Of course, parentheses are another kind of feature that you can use. Growth factor, beta is here kind of in parentheses, so this is probably a left structure. And all kinds of other punctuation signs can signal. Another strong feature is abbreviation. So you have tumor necrosis factor, and you find somewhere on the web tumor necrosis TN factor. This tells you that those two go together. If you find it like this, tumor necrosis factor NF, this is probably a right structure, and so on. Another thing that you can look at is concatenation. So, okay, healthcare reform, you can ask the question, do you find more often concatenated healthcare or health reform, right? And it's clear which one you find. Or healthcare or versus care reform. So in the first one, you look at whether health modifies care or health modifies reform. In the other one, you kind of check the adjacencies. And then probably makes more sense to do it in the context of the third word. So do you find more frequently healthcare reform or health care reform? And you see which of the two is more frequent. And this can tell you what the interpretation should be. Internal inflection variety, bone mineral density, if you find kind of, internal inflection here or here, it tells you that it goes left or right. Another thing is sometimes the adjectives can be switched around. So if you have adult male rat, if you find on the web male adult rat, those are switched around, means that they are both modifying rat. So you probably have a right structure and so on. And of course, paraphrases. Paraphrases are very, very important. So if you ask somebody to tell you what is bone marrow cell, well, it's probably cell in the bone marrow, cells from the bone marrow. Kind of those are different kinds of paraphrases. What you can do is you can actually try to generate these paraphrases and to see how many times you find on the web this paraphrase. Cell in the bone marrow, maybe 61,000 times. And this predicts the left structure because it keeps bone marrow together. Marrow cells from the bone, okay, this predicts right structure, but just 12 times. And you can kind of put, instead of prepositions, different kinds of verbs there, or the copula, those are cells that are bone marrow and so on. And what you can do is you can just like sum all the paraphrases that predict left and sum all the paraphrases that predict right and see which quantity is bigger. Okay, how well does it work? There's a standard collection from Wower who has written a dissertation on this, you know, maybe like 25 years ago or so. And if you look at the adjacency models and dependency model, chi-square, this kind of the best that I could come up with using the web, you have 75% accuracy for the adjacency model in the dependency one, about 80% accuracy. But using those kind of surface features and paraphrases, in many cases, you can do much better. So, for example, concatenation triples, right? You remember healthcare concatenated reform or health and care reform concatenated. In this context, it's 96% correct. Okay, it only covers 32% of the examples, but the ones where for which you know you can actually find it concatenated in this way, you can be pretty certain which way it should go. The genitive markers are quite strong, 89% accuracy. Again, they only cover 14% of the examples, but still, those that they cover are very strong. Abbreviations are very strong, 87%. Surface features in general, 85%. Paraphrase, 82%. These are all stronger than, you know, those models. And if you put the whole things together, you can do much better. You can go to, on the average, 89% with full coverage. Now, what I want to stress immediately is that size matters, okay? It's not just about using all these kind of smart features. They just don't happen unless you go to the web. So we have experimented with Medwine, which is, I don't know how much smaller. It has maybe like 20 million articles over there, and I estimate it's probably a million times more than the web. And over there, looking at paraphrases, right, those paraphrases that I have described to you, here paraphrases on the web, 82% accuracy, 86% coverage, and in Medwine, only 9% coverage and 47% accuracy. So it's much, much worse. So you really, really need a lot of data. Okay. Can you apply this to other problems, right? So, so far I have shown you that this kind of non-compound interpretation can be moved from the middle group to the top group. Okay, prepositional phrase attachment. So by the way, in syntactic parsing, there are like three important problems. One is non-compound bracketing that I have shown to you, prepositional phrase attachment and coordination. Now I'm going to talk to you about prepositional phrase attachment and coordination. Okay, what is the problem of coordination? If you say Peter spent millions of dollars, and okay, here of dollars is actually something that refers to millions. And if you say Peter spent time with his family, here with this with his family refers not to time but to spent. Okay, you can see the ambiguity in another way. So for example, I eat spaghetti with sauce and I eat spaghetti with fork. Okay, those are different things, right? One refers to the eating, the other one refers to the spaghetti. So it's exactly the same kind of ambiguity, right? And the question is it this prepositional phrase of dollars or with his family, does it attach to the noun or does it attach to the verb? And this problem is typically represented as, okay, let's look at the configuration of the verb, the first noun, the preposition, the second noun, and now I need to decide, is this a noun attachment or a verb attachment? And it's a very, very important problem in syntactic parsing because this, tells you about, the connection between the words and can help with semantics in many problems. Okay, so using surface features and paraphrases, we can achieve results that are, kind of comparable to the best supervised. Now, of course, the real problem is more complicated because when you have a prepositional phrase, there are many, many prepositional phrases it can attach to, to any verb and to any noun to the right, so there is much more ambiguity. Okay, about those n-gram models, what you can do in this problem, you can do the same kind of things. You can say, oh, okay, is the association between the pronoun or the first noun stronger or the association between the pronoun and the verb? And you can do these kind of things using, again, how many times I see the preposition and the noun together or the preposition and the verb together, maybe normalize, maybe chi-square, maybe probabilities, and those are kind of, the old models that people have been using. You can also use surface features, but I'm going really to focus here on the paraphrases that use linguistic intuition, because I think that, this is an important information source that can help you. Okay, here's one thing that you can do. If you have a configuration of noun, preposition, second noun, you can try to turn this into a noun compound. Okay, meet demands from customers, you can try to paraphrase as meet the customer demands. If you find on the web this kind of paraphrase, it tells you that you have a noun attachment because you are doing transformation within the, the noun phrase. Another thing that you can do is, okay, if you believe that you have a verb attachment, okay, so you have a verb, you have direct object, indirect object. Sometimes the direct and indirect object, you can switch them around. Had a program in place, had in place a program. If you can do this around, this reordering, this tells you that actually you have a verb. So basically, what I'm doing here is, a formulation of a linguistic hypothesis using linguistic knowledge, and then kind of, you do the transformation and you check, okay, how many times do I see this on the web? And if you see it sufficiently number of times, this actually gives you evidence that you should, make a particular kind of decision. Another thing that you can do is, okay, if you believe this is a verb attachment, then you can try to extract this preposition of phrase in apposition. Give an apple to him, I gave an apple to him, it was to him that I gave an apple, right? So you extract to him in front. Or if you think it's a verb attachment, then you can try to extract the whole thing in apposition. Shaken, confidence in markets shaken. Another thing that you can do is you can try to replace the first noun with a pronoun, because pronouns don't take prepositional phrases as arguments. Like put a client at odds becomes put him at odds. And this, if you can find this on the web, then sufficiently enough, this is something that supports a verb attachment. Another thing that you can do is you can substitute the verb with the verb to be, because the verb to be does not take an indirect object, it takes only one object. So eat spaghetti with sauce becomes is spaghetti with sauce, and now this with spaghetti with sauce cannot really attach to the verb to be, so this has to be a noun attachment. Okay, it's something that signals. Of course, all these things can fail and all that, but you're kind of using all these kind of paraphrases and together with other kind of sources of information and the simple associations and the surface features, and you put all these evidence together into one classifier, and you're trying, to make a prediction. Another problem, again related to noun compounds, but in general to coordination, is this is the third most important and hardest problem in syntactic parsing. So in the Pentry bank, this is syntactic annotation of English. You have, when you have bar and pie graph, you have this kind of flat structure. You have one noun phrase, and this is a noun, coordination, conjunction, another noun. But when you have president and chief executive, you have a different kind of structure. This is a noun phrase, this is another noun phrase, and then there's a noun phrase on the top. Why? Well, this is the way to encode in the Pentry bank the fact that bar and pie graph really means bar graph and pie graph. Okay, so this graph missing over here. This ellipsis. This is called ellipsis in linguistics. When you're missing, where you're omitting one word that is supposed to be there. President and chief executive is not president, executive, and chief executive. President is one thing, chief executive is a second thing, and you put them together. Okay, so if you do syntactic analysis, when you see bar and pie graph, you have to generate this structure. If you see president and chief executive, you have to generate this kind of more complex structure. Okay, so you need to make the decision when to generate what. And of course, coordination, can be much more complicated. So here's a real-world example, right? The Department of Chronic Diseases and Health Promotion leads and strengthens global efforts to prevent and control chronic diseases or disabilities and to promote health and quality of life. And now go figure out, what is the scope of each coordination and so on and so forth. And there are, gazillion of problems. And here this all really means and so on and so forth, right? This is what a real parser has to solve, right? And I'm going to talk now about the special case, of this particular configuration. Okay. Of course, you can go and look at the associations between individual words, and you can also use kind of simple surface features. But the most interesting problem is probably using, again, formulate a hypothesis using linguistics, and check this on the web. This is really going beyond the simple n-grams. Okay, one thing, if you have bar and pie graph, right, there's ellipsis. Well, if there's ellipsis, then kind of the coordination is at the level of bar and pie, then maybe you can switch them around. You can see, okay, do I find on the web pie and bar graph? Okay, if you can do this, then probably you have coordination, you have ellipsis, because the coordination is the level of bar and pie. If you don't have ellipsis, well, president and chief executive, then you can like coordinate, kind of switch around the other things, because now and applies to the whole thing. So you can like switch around chief executive and president. Another thing that you can do is, okay, if you think there is ellipsis, something is missing, okay, let's try to put it back, right? Bar and pie graph, you can go and look on the web for bar graph and pie graph. Or you can put it back and still switch them around. Bar and pie graph becomes pie graph and bar graph, okay? Those are kinds of things that you can formulate. And what I'm doing here is I'm using linguistic knowledge to do some kind of transformation, then I'm using the web to check, whether this is valid or not. So other kind of syntactic applications that you can do is, again, this kind of pantry bank. It has some kind of structure, and you might want to augment it. So especially when you have a noun compound, you want to see whether this is a left structure or right. So basically, what I have done for the noun compound bracketing, has been applied to the entire pantry bank. And this is something, okay, I'm going to skip this because there's too much linguistics here. Kind of a more intuitive example, it's query segmentation for information retrieval. If you go and you type in Google, tumor suppressor protein, right? No quotes, nothing, just those 3 words. The question is, how should the search engine interpret this? Should it insist on finding tumor suppressor protein as a string, those 3 words next to each other, or should it look for just backup words, just like I want a page that has tumor, that has suppressor, has protein, I don't care what is adjacent to what, or should it say, no, I want tumor suppressor together and protein can be apart, or I want tumor and suppressor protein apart. And basically, right, if it, it has to understand how to segment, how to execute this query to give you better results. And this is very similar to bracketing. In bracketing, you have those 2 options. In query segmentation, you also have two additional options. And this is something that other scientists have done, have applied to query segmentation using some of the surface features that I have introduced to you earlier. And those kind of things have been applied to full syntactic parsing. And okay, this is probably too technical, but in any case, it turns out that 40% of the improvement comes from just word associations and 60% from paraphrases. So kind of those kind of paraphrases are important. Let's go now a little bit to semantics, kind of to the interpretation of what a noun compound really means. So traditionally, the semantics of a noun compound, here I'm going to focus on 2-word noun compounds like malaria, mosquito, or olive oil, or water bottle, has been using abstract relations, say like malaria, mosquito is cause, olive oil is source, Lauer has just said, no, you don't need those abstract relations. You can do it with prepositions. Malaria, mosquito is mosquito with malaria. Olive oil is oil from olives, right? That's probably nice because it's directly usable as a paraphrase. But there are some kind of ambiguities. So we have kind of a flight in the morning, but flight at night. So you have different prepositions, but pretty much the same meaning, right? And so on. So what I think works much better is if you do the interpretation using verbs, because verbs are much more fine-grained and can capture the semantics better, and they're also directly usable as paraphrases. So, and then not using one verb, but using multiple verbs and the distribution of our verbs, this can actually explain better what is the relationship between the nouns in a noun compound. Okay, for example, what is malaria mosquito? Well, that's mosquito that carries malaria, spreads malaria, causes malaria, transmits malaria, brings malaria, has malaria, and so on. What is olive oil? Well, it's olive that comes from olives, is obtained, is extracted from, and so on. How do you get those paraphrasing verbs? Okay, you use the web, of course. How do you do that? Well, you use a linguistic trick. Here you have malaria mosquito, right? This is a modifier. You transform it into a post modifier. This pre-modifier becomes a post modifier. So you look for the pattern mosquito, that star malaria, and you collect the verbs that go in the place of this star. So you end up with, carry, spread, cause, transmit, bring, have, and so on. Okay, how does this compare to to other things in the literature, okay, let's say here's an abstract relation like source, okay, olive oil, okay, it's olive that comes from, oil that comes from olives, is obtained from olives, is extracted from, is made from, is produced from, is released from. So you see that kind of the verbs that we extract automatically are good paraphrases, tell you, you know, what it actually means. Now, malaria mosquito is supposed to be cause as an abstract relation, but okay, you have cause is responsible for, and so on, but this also carry, spread, transmit, which I think actually paraphrase well the compound of malaria mosquito, but they don't really kind of express cause. Why? Because if you think about it, the mosquito doesn't really cause malaria. It's a virus that causes the malaria. Mosquito is only transmitting it, and so on and so forth. So what I'm trying to say here is that if you go to the abstract relation, you're kind of losing some of the fine-grained semantics. Actually, you can see it here. It's olive oil, okay? It's oil that tastes like olives, okay? So this is not really source, but it's a valid paraphrase. So actually, there is something fine-grained that might be useful for interpretation. And so we have compared those automatically extracted paraphrasing verbs to verbs proposed by human judges into the distribution, and you know, there's kind of 32% cosine correlation. And there has been a shared task at SEMEVAL on trying to predict those paraphrasing verbs for noun compounds. Now, going a little bit to lexical semantics. In lexical semantics, there is a nice way, very popular way, to organize, to kind of explain the semantic of a noun. For example, what is a man? Well, a man is using the so-called componential analysis. So you kind of decide on some kind of components, and then you describe the nouns, kind of the notions in terms of whether they have these components or they don't have them. So for example, man is animate, human, male, and adult. Woman is all this but not male. Boy is all this but not adult. Boy is all this but not human. Very nice, right? You can kind of compare them based on different criteria. And you can actually do a similar kind of thing with noun compounds. So for example, here, I have several kind of compounds: cancer treatment, migraine treatment, wrinkle treatment, hair treatment. If you think about it, they are all kind of expressing the abstract relation treatment for disease. You have medical condition and you have some treatment for it, right? But kind of at the abstract level, they are the same. But if you look at the paraphrasing verbs and if you look at them as components, you see interesting things. So for example, okay, you can treat cancer, you know, you can cure cancer, but kind of, okay, let's say the wrinkles, right? You cannot cure wrinkles, you cannot prevent wrinkles, very interesting. But you can reduce wrinkles, you can smooth them, and so on. You can reduce migraine, you can prevent migraine, and actually, so you see kind of, you know, some finer grained distinction between those three. And then you also see, you still see that those three are very similar, kind of similar between themselves and very different from herb treatment. Herb treatment is continuous, you know, it doesn't really share verbs with the rest. What I'm trying to say is that if you use paraphrasing verbs, you get to much more fine-grained semantics, which might be useful for different things. Okay, what can it be useful for? Okay, going back, trying to put together the syntax and semantics. If you have colon cancer tumor suppressor protein, right, you have some particular syntactic interpretation, maybe bracketing. Oh, it's colon modifies cancer, tumor modifies suppressor, and also tumor suppressor modifies protein, colon cancer modifies tumor suppressor protein. And if you believe in this, you know, interpretation, then this tells you where the relations are. Oh, there's a location relation, maybe at the abstract level between colon and cancer, and purpose between tumor and suppressor, and agent between, you know, tumor suppressor and protein, and so on and so forth. If you believe in kind of, you know, prepositions, and then you can like paraphrase it in this way. Oh, it's protein that is a suppressor of tumors in cancer of the colon. And if you believe in verbs, right, you can put here a particular paraphrasing verb that is consistent with this syntactic structure. Oh, protein, what is, and you can actually fully explain what colon cancer tumor suppressor protein is. Oh, it's protein that acts as a suppressor that inhibits tumors, which is implicated in cancer that occurs in the colon. Okay, you might not necessarily need to spell it out. You might want to keep some of those together and paraphrase only part of them. But this gives you many, many different paraphrases. And actually, when I say many, it's really many, because here you have inhibit, but it can be prevent from growing or stop from developing. And I mean, you can like, remember, you have a distribution over paraphrasing verbs, so you can put many, many of those. And the nice thing is this, in this way, you end up with different paraphrases. So which means that you can understand that, okay, here you have this string, and here you have another string, and I know that they mean kind of the same thing. Of course, those kind of paraphrases are not necessarily limited to paraphrasing verbs. They're kind of, we have studied the problem of, okay, how do people explain different things like onion tears? Oh, it's tears from onions due to cutting onions. Here you have tears that sometimes fall when onions are chopped. So you see some material coming after. So it's actually, I mean, what I'm trying to say, semantics is much more complicated. If you try to explain what something is, okay, most likely you're going to go to paraphrase that uses verbs and prepositions, but sometimes you want to go to something more complicated. Okay, verbs, prepositions, coordinating conjunctions are very important in general, and you can like build a kind of semantic vector that tells you what is the typical relationship between two words, which can be useful for different things. So for example, okay, committee member. Okay, so here we have frequencies, we have the particular feature, which is like verb, preposition, or coordinating conjunction. We have the part of speech, which of these is preposition, verb, or coordinating conjunction, and the direction. Okay, how do you read this? Okay, you have a member of a committee includes members, member serves on a committee, member chairs a committee has members, committee consists of members, committee comprises members, member sits in a committee, committee is chaired by a member, committee appoints a member, and so on. Basically, you see typical things between a member and a committee, right? So you kind of can characterize the relationship between them. And you can use this to do different kinds of prediction of abstract relations, and this works quite well. You can also do this, use this kind of semantic vector to solve SAT analogy questions. Have you seen those? Okay, so I mean, how many of you have seen these as analogy questions? Okay, not so many. Okay, let me explain to you. So you are given something like ostrich is to bird, a swine is to cat, or goose is to flock, and so on, and then you need to select which of those pairs is in the same relationship as those, okay? So what you can do is you can say, okay, I have here two words. Let me build a semantic vectors that characterize the typical relationship between those two, and then I'm going to build another vector for this pair, and I'm going to see, okay, how similar those two distributions are. And then I'm going to build another one for this one, and then, okay, how similar they are, and I'm going to pick the one that is kind of the closest. You know, the best previous published results is 67% correct, and this one is 71% correct using these kind of vectors. And you can do it, you know, apply to other kinds of semantic tasks. I'm going to switch this into different kinds of paraphrases. So, for example, okay, this is a textual entailment task where the task is this. You're given this hypothesis, okay, this text, and here you have a hypothesis, and you need to tell whether this hypothesis is implied from the text, while preliminary work goes and the blah, blah, blah. And here, if you want to do this kind of implication, you need to realize that Geneva headquarters of the WTO is the same as WTO headquarters are located in Geneva, okay? And if you think about it, both are different paraphrases of the same noun compound, WTO Geneva headquarters, okay? You can fully paraphrase as headquarters of WTO, World Trade Organization, are located in Geneva, and then here you have one paraphrase, here you have another paraphrase. So you can use these kind of things to solve that. Going back to machine translation, right? You can use these kind of things to improve machine translation. Okay, how does machine translation work? Machine translation today is statistical. Typically, it works from the from wife examples. You are given, say, a sentence in English, a sentence in Spanish, and then and you give many of those examples, and then the algorithm tries to automatically infer which word is translation of which word, which phrase, short phrase is translation of which short phrase, assign them probabilities, and when a new thing to be translated comes, it tries to put them together. Now, how do systems like that translate noun compounds? Suppose that you want to translate from English into Spanish. Spanish is a little bit like Bulgarian. It hates noun compounds. So all price hikes, I mean, this is going to be paraphrased like, translate as, for example, alzas en los precios del petróleo, kind of you use prepositions in between, or Japan's economy, la economia nippona. So here, I mean, or you're going to use adjectives. It doesn't really like putting together now so much. Or here, export growth, crecimiento basado en las exportaciones, which is like growth based on export, right? And if you are going to generate this from those compounds, it's very, very hard to come up with this translation because you have to select the particular preposition and maybe the definite article or the particular verb, and it's very, very hard. And how do machine translation systems do it? Well, they work at the phrase level. So they just memorize, okay, maybe in the training data I have seen many times that oil price hikes is translated as alzas en los precios del petróleo, and I just memorize it, okay? So if at test time I see oil price hikes, I know that this is generated in this complicated way, but I just memorize it. Now the problem is, what if at test time you don't see oil price hikes, you see hikes in oil prices, okay? It's pretty much the same thing. It's a paraphrase of the same noun compound, right? But you're not going to match it. You have a pattern matching because you know how to translate all price hikes. You have this nice translation for it, but you don't know how to translate hikes in all prices. But we know it's a paraphrase, right? So what you can do is you can just say, okay, I have this noun compound. I can paraphrase in all possible ways using the techniques that I have described to you so far, and I just can go there and augment this translation table. I can just say, look, if you see all price hikes or hikes in all prices or hikes in prices for oil and so on, all these are going to have the same translation as all price hikes, okay, and vice versa. And actually, you know, in this way you automatically augment what you can learn from the actual text. And you can do it also recursively. You can actually paraphrase not the rules, but you can paraphrase sentences, and you can learn from that. And basically, what you get as a result is improvement equivalent to the improvement that you get, half of the improvement, or 1/3 to 1/2 of the improvement that you get from training on twice as much data, which is good. You kind of get it for free. Okay, and this kind of concludes the first part, kind of the probably more technical part of my talk. And then there's going to be a little bit less technical, and in the end there is going to be some futuristic provocations. Okay, so what we have done so far, right? We have talked about syntactic tasks, noun compound syntax, preposition of phrase attachment, noun compound coordination, the three kind of hardest problems in syntactic parsing, and we have also talked about some semantic tasks, and we have shown how these ideas can be applied to a real world task. And this was all kind of mostly focusing on noun compounds. And basically here the idea was to go beyond the simple n-grams, to go beyond counting words and pairs of words, but kind of looking into surface markers, into paraphrasing, using some kind of linguistic knowledge to formulate hypotheses and test them on the web. Okay, here I have plenty of references that I'm going to skip now. And now we go to, you are probably interested in a little bit what implications, at the end of the day, right, we are still using kind of some frequencies that come from the web, some kind of n-grams. And they're interesting questions. One of them is stability over time, right? So if I do something today and I do it tomorrow, right, the index probably has been updated and I'm not going to get the same thing. The question is, does it matter? So I have done some tests at different time. I have some newer results, but I didn't really include them here. So those are the different kinds of models that we have done for the noun compound bracketing. The mutual information, the concatenation adjacency, the reordering, the apostrophe, the genitive markers, the abbreviations, the internal inflection variety, kind of all these kind of models that I have introduced at the beginning. And we have here, the accuracy over time using Google using the Google search engine. And basically, there is some variety over time, but none of this is statistically significantly different. And this is using MSN, This is kind of how Bing was coded at the time, and only in one case there was statistically significant difference. So most of the time it doesn't really matter. So even though the counts that you get, the absolute counts can differ a lot, what you're interested in is whether this number is bigger than that number, right? And even if this number has changed a lot, this number has changed a lot too, what you are kind of interested in is the bounce between the two, and this doesn't really change so much, which is good. Okay, and then I have here comparison between different search engines. It pretty much doesn't really matter which of the search engines you use. In some cases, some of the search engines, only for some of the models, it kind of matters. Overall, right, what I can say is it doesn't really matter so much the fact that the absolute counts fluctuate. I mean, okay, from a research perspective, you can be very, very concerned about this because the results are not reproducible, right? I publish something, I get some result, I get some number, and I tell you, okay, this is 78% correct. You replicate in 1 month, you cannot get my 78% because the search engine index has changed, right? And this is not good because what kind of science it is? I mean, if I write something, you cannot come and verify my results. The good news is that typically if you do it, you get better results because the engine, kind of search engine has kind of improved. And you know, I have done it in the past, right? I have done it many times, and typically I have been getting results that are better than what the original researchers have been doing exactly the same thing. So it's not so bad. I mean, but it's not like physics, right? Where you, okay, how long does it take to fall down, and I do it again. It should be reproducible, right? So, but the point is, it doesn't really matter. If it matters, if it changes, it's kind of for good. That's good. Now, in practical terms, right? We are talking about search engines and Google. I mean, we have already kind of talked about that scientifically it's not reproducible, and there has been this criticism by Adam Kilgore, Google, which is bad science and all that. In practical terms, it can be solved. I have been showing to you, oh, let me paraphrase this in all possible ways, try all kinds of prepositions. This can be sometimes millions of queries just to solve one case. I mean, and they can cut you, they might not like it. So what can you do, right? You don't want to query the search engine directly. I mean, I have done it in the past. There was a time when the entire campus of Berkeley was cut off from Google and so on. So you don't want that, right? So what people started doing it a lot. I mean, this kind of became a trendy topic. I mean, that's exactly why Adam Kilgore has written this article, Googleology is bad science, because there have been a lot of people going in this direction, right? He is saying, okay, guys, try to be a little bit more smarter about how you're doing it. So Google has released n-grams. It has said, okay, guys, okay, you want all the n-grams. Okay, what is an n-gram? It's like a sequence of n words sitting next to each other in the web. You said, okay, so here's how many tokens. Tokens is like individual words of text. It's what, 95 billion sentences. Here's how many, 13 million individual words and 314 sequence of 2 words and like, you know, about 1 billion sequence of 3 words and so on. And he said, I'm going to give to you those and also the accounts on the web, which is great, right? And people have started using this instead because now we have a sample. The problem is that they have discarded all n-grams that appear less than 40 times, and in the n-grams they want each of the words to appear more than 200 times. The thing is that there's a zip Powerwall kind of distribution, so this means that they have eliminated, I mean, they have given, I don't know, much less than 1% of the data. So, and actually the most interesting thing is, but the thing is, even this is very hard to index. It's very big. I mean, where do you store it? I mean, if you want the whole web, I mean, you need a supercomputer, right? I mean, so you don't really have the computational power to do it. So they have been, another thing that they have worked on is version 2 of the Google n-grams. So there has been like more preprocessing, kind of duplicates were removed and so on and so forth. And another interesting thing is they had like part of speech. So twice, they say, they don't just tell you, they tell you, okay, twice is seen on the web that many times, but it's also kind of, oh, as a noun, in plural noun, that many times, and as a verb, you know, that many times. So now you know how many times it was a noun, how many times it was a verb, which might be important. So, for example, if I want to do kind of some compound bracketing, right? Twice I need to know whether I'm doing the right counts, because I don't want to count it as a verb. I might want to count it only when it's noun. The problem is this was never been publicly available. They published research about, kind of research publications about it, but they never made it public, okay? So all that we have now, if you don't want to crawl the web, is this. And this is back from 2006, okay? Now, this is a problem because web is very dynamic and gets outdated. So what Microsoft has done, they have also released engrams, but they did it in a better way. So they have kind of created a service for you, okay? So what are the problems with the Google engrams? There are some small minor issues like non-standard tokenization, how they are handling hyphens, and of course this is important. If you don't do it in the same way, you don't get the right counts, and of course this truncation of the counts, and of course the files, they are 24 gigabytes gzipped, right? Okay, maybe not so big anymore, but in 2006 it was. You know, how do you index it, how do you use it, and all that. But the more important issues is, first of all, there is no distinction between where this engram, this word is coming from. It is coming from the title, from the body, from the anchor text, and this is very important. And then it's a dead corpus. It's corpus dated in 2006. It's frozen in time, and you know, in fact, the web is quite dynamic. Okay. He's about mixing data, right? So if a word appears in the URL, it tells you something. I mean, about its importance. If it's coming from the HTML, from the kind of heading, from the caption, from the body, and all that, and those you might want to kind of use these differently. The second thing about dynamics of the web, right? There has been this experiment by scientists. So okay, they start with some index. Okay, we create an index. You index the web, and you look at this. I think was done in Microsoft. You kind of index the web in September 2008. Okay. And then in October 2008, your crawler has crawled new things, has added some new pages, and you say, okay, let me see single words, how many new single words I have, right? I mean, you have vocabulary, right, the unique words in your index in September, and you see kind of, in the new pages that you add within 1 month, you kind of build another dictionary, and you check how many of those, of your new dictionary of individual words has changed. And it turns out that of the new words that you add, 70% of the new vocabulary that you have indexed in October has not been seen in September. Okay, so 70% of the words are not in your index. Those are probably names of companies or of locations or of new products and so on and so forth. And a similar thing with bigrams, trigrams, fourgrams. Those are sequence of 2 words, 3 words, 4 words. This tells you how dynamic the web is just from 1 month to another. Think about it, what happens in 2006. I mean, Prose doesn't have many new things like iWatch or ISIS or who knows what. Okay, so what Microsoft has done, right? They have created these web engram services, okay? So they tell you where the engrams are coming from, whether they are coming from the body or from the title or from the anchor text. Then kind of, if you just look at the absolute counts, they might not be good. You might need to have some kind of smoothing. They have all the documents index on the US market, and then they do periodic updates. It's not live all the time, but maybe like every month or 2 months or 3 months or something, they kind of do an update to the service. And now you can just go and query it and get the engrams and get exactly what you need, and it's nice. And so here I have an application, example application of word breaker. You want to build this application. When you have 1-800 flowers, you want to break this into 1-800 flowers. 24/7 moms, you want this to be 24 space 7 space moms, right? Those kind of things. Or München airport, you want München and an airport, or parlez-vous français, you want, break here and break there, those kind of things. And here is, okay, different kind of models, right? They try to do this kind of task. And here is when you use, using frequency of single words, pairs of words, triples of words, and when you do it using the body, the title, the query, the anchor. And basically you see, okay, so if you use unigram single words, it's best to look at the title and the query, and then if you do it with trigrams, with the title. And in any case, what I'm trying to say is like, it matters, right, where it comes from. So the conclusion from this is, okay, there is no data like more data that can be correctly exploited. Another thing that Google has, okay, they have done something to improve. So what they have done, that they are like indexing, they have these Google book engrams. They have these Google books, right? So far they have indexed, kind of scanned and digitalized 6% of all books ever published, which is a lot. And what they have done is they have done part-of-speech tagging and had also dependency parsing, had modifier relations. And you can do it kind of to study different kinds of linguistic trends and so on. So basically when you have the dependency, John has short black hair, you have, black modifies hair, and short modifies hair too, and has as arguments John and hair and all that, and those are kind of nice things that you can do. So you have the syntax, and you know that, this is an adjective, and so on and so forth. And on top of this, it's available in different languages. So the Microsoft thing was available in English. So, and of course this grows, how many tokens you have and all that. And now you can actually not count words, you can count things that you care about. I mean, you can, okay, you want to see read book, right? Book as an argument of read. And you can, okay, how do you express this? Book as an argument of read. How many times I see it, in the literature? I mean, what kind of things people read? Well, if you just go with words, engrams, you can say, read this book, or read a book, or read the book. You have to go enumerate those. Or with book engrams, we can say, no, I want read any determiner book. You can query for this, which is much better. Or you can say, no, I want book as a syntactic argument of the verb read. Okay, I want it to be, kind of an argument of read. So you can directly ask for this, which is much, much better. Okay, for many purposes. And you can see that kind of the counts that you get with just those, right, are quite small. And if you look at this, it's quite different. You get a different picture. And you can do different kind of semantic analysis, syntactic analysis, and so on. Okay. The last thing before I go to the future, right? The last thing about the present is that the web is not just a web of text. The web has other things. One of them is images, right? And suppose that you want to build a dictionary that tells you, translation dictionary between English and Spanish, right? And so if you look at the images for cockatoo and cacatua in Spanish and in English, you can actually notice that the pictures that you get as a result of this query, and as a result of this one are kind of similar. And if the images are similar, probably the words are about the same notion, right? It's very nice and very interesting. There has been a lot of research in that direction. So the same thing for turtle and tortuga, or Kendall and Bella. And so what you can do is, you can just compare images. How do you compare images? I mean, okay, you can say, do I get the same image as a result? Maybe you are going to do it. Or you can do kind of a little bit of analysis. One kind of analysis of an image can be a color histogram, right? How much yellow and green and whatever I have in the image. Or another thing that you can do is you can look at sift points. It's kind of, some statistical algorithm that tells you the most important characteristic points of the image, which is used a lot in image recognition. And then, okay, you can compare, this image to this image or to that image and so on. And kind of you can say, the most similar image to this one is this one, right? Based on those kind of sift points or color histogram and all that. And what can you do with these kind of things? Okay, you can kind of build a dictionary that tells you, cockatoo and cockatoo are kind of the same thing, or turtle and tortuga. Another thing that you can do is you can answer interesting questions like, okay, can you eat migas, or can you eat carillon, or can you eat mami, okay, whatever this means, right? How do you do that? Well, migas is, if you do a search, you get this kind of thing. There's probably something edible, it's fruit, and carillon is, something else. Okay, so what can you do? We can say, okay, I have migas, right? I have a query for migas, and those are the pictures that I get back, right? And then I extract features from there and I build a vector, right? And now I want to say whether you can eat migas or not. Okay, maybe from training data, I have kind of a vector of the things that you normally eat. Okay, so you have the verb eat, and you have the things that you eat, and you go and you kind of look for the images, and if you go with all kinds of things that you eat, you are probably going to learn in this vector that, the things that you eat are probably circular plates or fruity covers or a particular kind of texture and so on. And then what you do is you use this kind of pre-word vector for the word eat, right? That is kind of looking into the images of things that are typically eaten. And then migas comes, you look at the pictures of migas, right? And you build another vector and you kind of take the dot product and see whether you get a high number or you get a low number. If you get a high number, this means that, the kinds of things that you see here in the pictures are the kind of things that the verb you see normally for things that are animal. And I'm ending here this part, and I'm getting probably to the final part of this talk. It's about the future. Okay, so far I have talked about things that people have been doing. Okay, let's take a step back, right, to the big dream of computational linguistics, right? You want systems that can understand human language, okay? And what we have talked a little bit about, I mean, if you want this dream to come true, okay, there are probably two things that you need to do. I mean, you want to solve semantics, which is kind of meaning. You want to understand what the text is about. And I'm going to talk a little bit about semantics, because this is critical for the overall advancement of the field. And I'm going also to talk a little bit of a particular application, namely machine translation, because it's practical, it's within the reach of the current technology. Okay, let's look at semantics first. So if you want the kind of the big dream come true, what we need to do is we should not be looking just at statistics, how many times I see this word, that word, even on the web. I mean, you should go to the deep meaning of text. And basically, we should not be really looking at words. We should be looking at the meaning is not in the words. The meaning is in the relationship between the words. So we should be looking at the semantic relations. We should be looking at also at the way that words combine multi-word expressions, because they cover 70% of terminology. That's my opinion. And I think that the semantic revolution is definitely going to work at is going to use statistics from the web scale. This is not going to go away. But I think that what we are missing is some linguistic knowledge, some kind of intelligent way to, inject things that we know about language. And by the way, there is now a lot of interesting research that tries to combine language with those images or with video and so on and so forth, because this is how we learn language, with interaction. I have a child 2.5 years old. I tell him, oh, look at the car. Oh, he knows this is now a car. Okay, maybe after a couple of examples like that. So there has been like this corpora list, which is an important list in computational linguistics. There has been recent discussion on moving lexical semantics from alchemy to science, and this is where semantics is. So the question is, can you do that? I mean, Chomsky has done it already to syntax, because syntax, like 56 years ago, it was the same thing. It was a mess, it was an alchemy, it was all kinds of people writing about this particular problem that they think is important. But, I mean, he tried to do syntax into a math. He started inventing those kind of formal grammars and all that. The question is, can you do this with semantics? Now, semantics for a long time has been a marginal area, right? There was very little research in that direction, and this is now changing a lot. And I'm going to tell you why this is changing. But before that, so this is from a conference from a month and a half ago, which took place in Denver, Colorado, the North American chapter of ACL, one of the top conferences in our field. And this is the distribution of papers submitted, the whole thing. The rate is rejected and the BOO is kind of accepted per area. And now you see that semantics is the biggest one. And this is something new. Semantics used to be here, okay? Which means that people are now paying serious attention, which means that if the best scientists, and most of them are working in this area, this means that they see some promise, and something, if a lot of smart people are putting efforts in this direction, we won't kind of expect something to happen there. I mean, they also expect something to happen, otherwise they are not going to waste their time. For many years, machine translation was number 1. Now it's number 3. It's still quite popular. Number 2 is social networks. That's understandable. Now, turning to machine translation, it's a very interesting example. Again, talking about revolution. There have been two great revolutions so far. So for a long time, machine translation was purely rule-based. Okay, we have this rule, and a lot of nice systems have been built. One of them is Systran, which was used in Bubblefish before in Alta Vista, if you remember those times, right? So they have invested more than 40 years of kind of really good rules between English and French. There have been some nice in Bulgarian, Bultra, where have been like a lot of manually encoded rules, which is quite nice. And IBM revolutionized the field in 1993 by proposing statistical machine translation, which was word-based at the time. This was a revolution because it was statistical for the first time. In 2003 came the phrase-based systems, which is like 10 years later, and this was another revolution. By the way, Google uses phrase-based system. This is the state of the art. This is what has not changed much since 2003. And when I'm talking about revolution, this is what is a revolution. This is like 10 years after 1993, the best system, one of the best system, from 2002, this is how far you can get with word-based translation. This is how far you get with phrase-based translation, where you don't translate word by word, but with phrases. Look here. Assistant Wednesday may record her trips to Libya tomorrow for flying. It looks like a word salad, not clear what it's talking about. And when you go to kind of phrase-based, you get Edgerter has tomorrow to resume its flights to Libya. Much, much more understandable, clearly visible, right to a human. This is what a revolution is, right? Okay, so we had a revolution in 1993, in 2003. So 2013 should be the next one, right? I mean, it's every 10 years. This is how it seems to be happening. And people have been thinking, okay, look, this kind of vacuous triangle in translation, very, very kind of nice thing from the textbooks. Okay, when you translate with words, right, directly you get, you are here in terms of performance. When you translate with phrases, it gets better. Maybe if you translate with syntax, it's going to be better. Or maybe if you go to the meaning, to the semantics, you're kind of going to get better. Maybe this semantics is kind of language independent, maybe some kind of logical form or something else, right? This is kind of the so-called interlingua. Okay, maybe it's going to be even, that's the holy grail of machine translation, which there are systems that work with interlingua, but they are just with using a few hundred words. It's not, doesn't scale. Okay, so maybe we're overdue, right? I mean, people talked, okay, there has been a lot of work on syntactic translation. It helps for some language pairs where there is a lot of difference, say, between English and Chinese or English and Japanese, right, where there is a lot of reordering and all that. It's really needed. But if you're translating between Bulgarian and English, it's not really needed because the structure of the sentence is not so much different. Even between, say, English and Arabic, it's not so much different, so it doesn't really help you much. Semantics, it's not exactly solved yet. So, okay. So there was no revolution. We are kind of overdue. Actually, we are probably now into the third revolution of machine translation. Yet to be confirmed. Last year, the best paper award at ACL, the best conference in our field, came from a company called BBN, where they have demonstrated in terms of automatic evaluation measures, improvements, right, for machine translation, that at least looking at the numbers look like this. The improvement from here to here is, in terms of automatic measures, is similar to the improvement that they have from this kind of phrase-based to this kind of, semantic kind of neural network-based. And so it's very interesting about neural networks. Neural networks have been around for quite some time. And every 20 years, they get kind of abandoned and then they get rediscovered and so on. And now we're in the next kind of neural network revolution. I would even say a bubble a little bit, but it has already revolutionized speech recognition 2-3 years ago. Now kind of the best systems in speech recognition are using neural networks. Everybody has moved into that direction. For machine translation, okay, it improves, but not so much. The results by those scientists from BBN have not been fully confirmed. It's confirmed that it helps, but not as much as they have reported. But of course, those are very complicated things with many fine-grained parameters. So people believe in it, go in that direction, but it's still kind of to be confirmed whether this is kind of a small evolution or a big revolutionary step. People have not switched there. For speech recognition, everybody is there. For semantics, everybody is there. There's strong evidence that this helps. I mean, for image processing, I mean, this has been, neural networks have been, you know, for a long time there. But for speech, people have been using other things like neural networks and so on. Of course, the questions are these neural networks, can they scale to the entire web? Can they use linguistic knowledge? Can they, you know, handle multi-word expressions and so on? Okay, so if you're talking about the future, from what I have presented, okay, the web, definitely there, semantics, linguistics, and maybe in deep neural networks. And of course, I can stop here, but there is a version 2.0 of the future, okay? Look at this sentence. Do you think it was written by a computer or by a human? Who thinks that's a human? 3, 4, 5, okay. Who thinks that's a computer? Okay, about 10, 15. Very good, that's a computer. So this is from, right? From March 2014. What about this one? Who thinks that's a human? Okay, maybe 10, 15 people. Who thinks that's a computer? About the same, probably a little bit less. Wow, you're good. That's human. Okay, what about this one? Who thinks that's a human? Okay. Who thinks that's a computer? Okay, about twice as many for a computer. Okay, that's a computer. I got this wrong. I thought it's a human. That's like from my, I mean, you can go online and do this test for yourself. Okay, you're good. 3 out of 3 so far. Wow. What about this one? Who thinks that's a human? 4 or 5 people. Who thinks that's a computer? Wow, everybody thinks that's a computer. Okay, this is a computer. This is written by a product by a company called Narrative Science that is doing those kind of things for news. Wow, 4 out of 4. Come on, you should fail on some. Okay, what about this one? Who thinks that's a human? Wow, pretty much everybody. Who thinks that's a computer? Okay, 3 people, 4, 5, okay. This is a computer, haha, okay. 4 to 1, okay. So this is, you know, a Russian novel called Triumph, written by a computer in 72 hours. Okay, so computers write novels today, okay. What about this one? Who thinks that's a human? Quite a few, okay. Who thinks that's a computer? About the same. Okay, again, who thinks that's a human? Okay, a bit more. Okay, who thinks that's a computer? A bit less. Okay, kind of equal. Okay, that's a computer. So it's what? 4.5 to 1.5. Okay, this one. Who thinks that's a human? Okay, computer? Okay, it's kind of a tie again. Okay, that's a human. This time it's a human. So, okay, it's 5 to 1. Okay, no, 6. It was 4.5 to 1.5, so it's like 6. Okay, 5 to 2. It's 5 to 2. Okay, here, there was one. Who thinks that's a human? Very few. Who thinks that's a computer? Many more. Okay, that's a computer. Wow, you're good. Okay, so you felt like once and twice kind of hesitating. Okay, you're good. When I did it, I was 4-4, but it was me. So there's a professor in INSEAD, a business school in France, called Philip Parker, who has written more than 1 million books, fully automatically generated, and he's selling more than 100,000 of them in Amazon. Okay. That's a big business. I mean, that's what they do in business schools, right? And I mean, there are companies that are, writing automatically news articles that we're reading today. And some of the, if you go on their websites, you see that some of the biggest publishers are their clients. So we are already consuming. They estimated by 2025, 90% of what we consume is going to be fully automatically generating. Okay, what is next? Fake reviews, or kind of sentiment analysis. I know that there has been like some talk about sentiment analysis. So okay, you have like computers write, how they feel about the new iWatch, right? And then other computers kind of analyze this. Oh, computers don't really like the new iWatch. We should do something else. I mean, and of course, then, okay, so in Bulgarian, computational linguistics is computer linguistics. It's more like computer linguistics. Maybe that's the right thing. I mean, maybe this is the future, right? So computers are going to write text, and other computers are going to analyze it, and they're going to write news and all that, and we can stay out of it. So it's going to be really computer linguistics. And, okay, there's a third version of the future, okay? Again, a little bit about translation. This time about humans, okay? I'm finishing, I just need a minute or two, okay? So, back in 1945, there was this, an ultimatum to Japan to surrender or to face destruction. And the Prime Minister said at a conference, no comment, we keep discussing. But the word that he used is ambiguous. It can mean no comment or we reject. And, kind of, this is one of the famous, potential examples of wrong translation because it was translated in a particular way and a particular thing, followed. So what is the future? Will the next nuclear war start because of a wrong computer translation? So Elon Musk, the guy who is, creating Tesla and so on, and has created PayPal in the past. I mean, he has tweeted this. We need to be super careful with AI, potentially more dangerous than nukes, okay? This is a nice graphic, right? So this shows the, how the computational power of a computer, of a normal computer that you can buy for $1,000, like a laptop or something, right? And it tells you that it's estimated in 2025 for $1,000, your laptop, right? Probably even your smartphone, is going to be computationally as strong as, the human brain. So this is going to be the tipping point. Another thing, there is going to be about 2030 something more robots than humans on this earth. And it might sound too apocalyptic and you probably don't believe it. And there are other people that don't believe in global warming. But truth is that, a few days ago, a robot has killed a man in Volkswagen company plant in Germany. And people are getting worried. I mean, Elon Musk has donated $10 million to the Future of Life Institute. There has been like a declaration by the leading scientists, both in academia and industry, doing artificial intelligence, calling for putting things under control, including with legislation and so on. Elon Musk says that, this is the biggest existential threat is artificial intelligence. So Stephen Hawking, the Einstein of our time, also thinks that full artificial intelligence could spell the end of the human race. And Bill Gates is also very, very concerned. Okay, so what is the future? Is this the future? Or maybe it's this? Or maybe it's this? Or maybe this? Or maybe this? Okay, thank you.
Very, very big thank yous to Preslav for this awesome lecture. It turns out that we're a bit pressed by time, so Now, I hope you have 3 very interesting questions. Who has ones? Okay, question? Yep. So,
Okay, so those are the questions. Okay, so how do I start? From the top or, okay, latest question, okay. From the top, okay. What does it mean 15% coverage, for example? Okay, 15% coverage, okay, I probably should have noticed this earlier. This is probably from the examples, right, with the non-compound bracketing. 50% coverage means that, you know, we have a particular pattern, right? You are testing a hypothesis, and this pattern just, you find 0 results on the web for this particular pattern, right? Which means that you cannot really, you know, say anything. There's no, I mean, doesn't much anything, which means that it's not really usable. 15% match means that, okay, this is how usable it is. Next question, how you can improve your sample if you are testing by chance with machine-generated text? Okay, so I guess this is similar to, if I get the question correctly, it's probably about spam. There's a lot of spam on the web, right? So there's a lot of computer-generated content, and this is something that I actually kind of have talked about even today, even in the news. This automatically generated content. If it's automatically generated, it's not clear whether it's linguistically trustworthy and all that. So this is a real problem. I mean, the kind of the hope is that if you have high statistics, those statistics are going to be more reliable. If you see, okay, if you have this pattern, right, you are deciding between left structure and right structure, and you have evidence for left structure from some pattern that happens 4 times on the web and right structure happening 1 time on the web, should you make a decision but just like, oh, this is 4 times more than this? Probably not. Those are kind of very low numbers. Chances are they spam and all that. But if it's like, I have 4 million times this, 1 million times this, then I'm going to say, you know what, this is probably a better structure. So this is how you can kind of, you know, fight spam. But it is a real problem. It's going to get more serious with time. Next question, how are the components for relational component analysis generated? Okay, this is about, okay. Okay. Here's the relational component, combinational analysis. Okay. So these components are actually automatically generated. Those are the verbs that are automatically extracted from the web. So the answer is those are automatically generated. And here's how, right? So we have mosquito, we have malaria mosquito. We go on the web and you look for the pattern mosquito that start malaria. Then we do syntactic analysis and you look for the verbs here, and we extract those verbs, and those are actually the components: carry, spread, cause, transmit, and so on. And here in the relational combinational analysis, the thing that I propose, you do it in the same way. You say, okay, cancer treatment is like treatment that start cancer, and you go and collect what are the verbs that happen there, and you end up with some verbs, and then you end up with some verbs for migraine and for wrinkle treatment, for hair treatment, and then you put them all together and you build this kind of graph. Let's see, other questions?
I think that was the last one from online. Are there any questions in the room? Okay, let's fix it. 2 people, 2 questions, because we turned out we are running out of time.
Okay, thanks for the great talk. My question is a bit more like a curiosity than something very specific or technical. If you think the analysis that you do, like known compounds, the relationships, and so on, has anyone in the scientific community tried to give a quantitative, some sort of numeric measure of how big a language is, for example.
How big a language is?
Yeah. Well, I mean, it could be 42 as far as I'm concerned. But, is there anything that comes back from all that research in trying to do, for example, machine translation that actually tells you something about languages, like the other way around? I don't know if you get the idea.
I mean, okay, so I'm not, you know, completely sure I'm getting the question right, but from what I understand, the question is about, is there anything from computational linguistics that can tell you how big a language is, say a particular language? So for example, is English bigger than Bulgarian or something like that? I mean, whatever big means, for example, right? This is the question? Okay, so, well, I mean, it's very hard to define big, right? Because if you ask somebody, they can tell you, oh, of course, English has richer vocabulary, right? The question is, how do you count, right? If you count the words kind of in their kind of normal form, okay, he's a noun, he's a verb, right? Then chances are that English probably has richer vocabulary than Bulgarian. But then if you look, because it's spoken by more people, so kind of, you know, more words emerge and kind of can borrow from contact with many more languages and all that, that's normal. But then if you count at the, you know, if you take inflection into account, you have a Bulgarian verb, it can have like 100 forms, maybe sometimes. In some cases, then you know, just from this one form, you can generate so much. And then this is kind of probably for some languages even not very well posed question, because okay, in theory, those things are recursive. So for example, noun compounds in German, I can generate as long as I like. I mean, I can just like keep adding things in theory, or agglutinative languages like Finnish. I can do a million words by just adding suffixes, and I can go on. Of course, people are not going to say this, but it's a word. If I give it to somebody, yeah, it is a word. So, I mean, how do you even count, right? I mean, if you have a corpus, right? So it's
this is
hard to
why I
count.
said it's more like a curiosity. Has anyone tried to make some sort of meaning like that? Just doing that kind of research and then maybe trying to ask some curious questions.
Right. I mean, those kind of counting, it has been done, but it depends on the corpus and all that. So, but this actually has an implication. So, if you look at, say, a text in German or a text in Finnish, right, of say of 1,000 words and 1,000 word tokens, and then you build the vocabulary there, kind of how many individual words, different words I have there, and if you do this in English or in Bulgarian or in French, you're going to find out that kind of, you know, Finnish is much more richer because you have many more, or German, right, because of those kind of long forms. Then the question is, do you want to translate with this, or do you want to kind of try to break it into smaller pieces? And this is actually one of the problems that I have mentioned, is kind of the segmentation problem. So it is a problem, right? So I mean, this is a source of vocabulary, and actually part of the reason why we want to analyze now compounds is exactly to kind of attack this vocabulary, reduce it a little bit, kind of, you know, it's okay. The answer is, if you translate from between German and English, it's fairly standard. I mean, everybody wants to break the compounds. Sometimes it's better to keep them together. Like in English, newspaper. Do you want to break it into news and paper? Sunday, do you want to break it into sun and day? Not so sure, right? So.
Okay, thank you. And last question.
Thank you. Preslav, I see in Qatar you work with Arabic. The focus of your research is in the Arabic language, right? Because you mentioned this in the beginning.
Not the entire research, kind of part of the research. I mean, so for example, machine translation, right? It has to have involved two languages. So I mean.
I see, but isn't Arabic language some kind of priority?
So
do you know some?
It is a priority. We're the Arabic Language Technologies group, but
yes,
but
just
kind of we do probably like about half English, half Arabic, and we also do other languages as well.
Because we don't see just single slide for the specific problems of Arabic language. Can you tell us some funny features of this language which are problems for NLP? Which
Not
is
in this
specific?
talk, but yeah, they are. Okay.
Like in German.
Let me show you a funny example. Okay. Yesterday I gave a talk in Blagoevgrad at the International Linguistics Olympiad, which, by the way, is the 13th in a row. Oh, first of all, let me show you example of Arabic, right? Which, by the way, is the third in a row. Okay, right? Here, see? Okay, here's Arabic, right? Okay, let me show you an example of Arabic. Funny thing. Ooh. Okay, I was telling about the 13th Olympiads it's kind of the 13th in a row, but it's the third time done in Bulgaria. By the way, Bulgaria is one of the strongest teams in this competition. Okay, right here, I'm going to show you. Okay, here, right? This kind of dish, okay, this is something called küfte, meatball in English, right? The thing is that in Arabic, it's right meat boo, right? And it sounds like po, sounds like boo, and actually meat boo in Arabic means po is dead. This is what it means. And kind of many people there think that this is an Arabic dish. Because, you know, okay, of course, this is kind of an Arabic dish, I mean, meatball and all that, they're eating it all the time. They don't realize it comes from English, so they now back translate. And, you know, meatball becomes po is dead because it really means po is dead in Arabic, right? And you see this, it's super massive. You see it everywhere. I mean, they just don't realize that this is, you know, not an Arabic word. So, yeah, I mean, there are problems like that.
Thank you so much, Preslav. Let's once again thanks Preslav for this awesome lecture. And thank you everyone for sharing this hot Thursday afternoon with us. If anyone wants to help with the chairs, you're welcome to stay and then have a beer with us and probably ask Preslav for more jokes about Arabic or other languages.
Yeah. So after we fix everything here, we'll be heading to the bar just opposite of the palace, of the art academy, of the art gallery, in the other part of the National Theatre Park. So you'll be welcome there. Mola? Na Mavzoleia, da.